In this example, in this video, we're going to do some examples using the power rule. The power rule states that if f of x equals x to the n, then f prime of x equals nx to the n minus 1. Now, we went through the proof of this, all these blue slides, in a previous video. And in this video, we're just going to go through some examples together. So in this first example, if f of x equals 4x to the 5, then I can simply say that f prime of x is equal to 5 times 4 equals 20, x, subtract 1 from the exponent, 20x to the 4. That's my answer. Next question, if f of x equals 11x to the 5 over 2, then f prime of x will equal, we'll have a coefficient of 5 over 2, whoops, we'll have a coefficient of 5 over 2 times 11, which is 55 over 2, times x. And then we're going to have an exponent of 5 over 2 minus 1. Well, what does that equal? 5 over 2 minus 1 ultimately equals 3 over 2. So that'll be our exponent on x. So there is our derivative. 55 over 2 times x to the exponent 3 halves. This next one's kind of interesting. If f of x equals 7, that's like saying 7x to the exponent 0. Well, let's take that 0, multiply it by the 7. Let's now determine the derivative. We take that 0, multiply it by the 7, we get 0x. And now we're going to subtract 1 from that exponent of 0. 0 minus 1 is negative 1. So I can say f prime x equals 0 times x to the negative 1. Well, that's the same as 0. And there's a lesson to be learned here, which is that anytime you have a constant function, where it's just equal to an unchanging value, the derivative of that constant function will always equal 0. So if you get this question, f of x equals 7, what's f prime of x? The answer is simply 0. Okay, let's try this next question. We've got 4x cubed minus 3 root x. Well, I don't have a method of determining derivatives when I have square roots, but I do have a method for determining derivatives when I have exponents. So what I'm going to do is change 3 root x to 3x to the exponent 1 half. And now what I'm going to do is simply determine the derivative of each one of these terms. 3 times 4 is equal to 12x. And then that 3, we're going to subtract 1 from it and get 2. Then I'm going to take this 1 half, I'm going to multiply it by that negative 3. I'm going to get negative 3 halves. And my exponent on x and my derivative will be 1 half minus 1. And that ultimately equals negative 1 half. And so that is our derivative. For this example, we're going to do it two different ways. Method 1 is going to involve us expanding out k of x. Well, k of x is equal to 5x minus 3 quantity squared. So it's 5x minus 3 times 5x minus 3, which is 25x squared minus 30x plus 9. Now I'm going to determine the derivative of that. K prime of x will be, we'll take that 2, multiply it by 25 and get 50. We'll subtract 1 from the exponent of 2, so we'll get a new exponent of 1. Now we've got 30x, which is like saying 30x to the 1. So I'm going to take that 1, multiply it by the negative 30. It'll still be negative 30, but I'm going to subtract 1 from that exponent, and I'm going to get a new exponent of 0. Now, x to the 0, we're going to call that 1. And then my last term is 9. The derivative of 9, we just said a while ago, we talked about how the derivative of a constant term will be 0, so we can call that 0. So I can say that this is the same as 50x minus 30 times 1 plus 0. So in other words, that derivative is 50x minus 30. So something that's worth remembering is this. If you have, like in this last question when we had 25x squared minus 30x plus 9, anytime you have a linear term, in other words, x to the exponent 1, the derivative of that term will simply be the coefficient. So in this case, the derivative of negative 30x is negative 30. And then anytime you have a constant term where there's no x at all, the derivative of that term will be 0. It just falls away. And then the derivative of this 25x squared term, well, we're going to figure that out using the power rule. Okay? Okay, now I could also do method 2 here. Method 2 is a little, we're kind of showing you ahead of time what the chain rule will ultimately look like. We're going to call it power of a function rule. What we're going to do here is I'm going to say, okay, I have, instead of x to the exponent 2, I have a function to the exponent 2. So what I'm going to do is I'm going to take that 2, I'm going to put it in front, just like I'm kind of used to doing by now. So k prime of x is going to be 2 times 5x minus 3 to the exponent 1, because I subtracted 1 from that exponent. But now, because it wasn't x to the 2, it was function to the 2, 5x minus 3 to the 2. Because it was function to the 2, I now have to multiply by the derivative of that function. So what is the derivative of 5x minus 3? It's just 5. And so k prime of x is going to equal 2 times 5x minus 3 times 5. Well, 2 times 5 is 10, so it's going to be 10 times 5x minus 3, or in other words, 50x minus 30. So when you get a question like this, you could expand it out if you want, but it's really, really good to learn this power of a function rule, or like we'll later call it, the chain rule, and then do it that way. And if you want to see why it's good to know that method, take a look at our next question. For our next question, if we don't know that power of a function rule, we're going to have to expand out this horrible polynomial raised to the exponent 6. Instead of doing that, let's use the power of a function rule. What we're going to do is we're going to take that 6, we're going to multiply it by the negative 3, we're going to get negative 18. I'm going to leave that function alone at first. And then I'm going to subtract 1 from that exponent of 5. Now, if the question was, what's the derivative of negative 3x to the 6, then the answer would be negative 18x to the 5. But that wasn't the question. It was negative 3 function to the 6. So my derivative is negative 18 function to the 5 times the derivative of that function. I have to figure out the derivative of what's inside here. So 4 times 15 is 60, subtract 1 from the exponent. 3 times 8 is 24, subtract 1 from the exponent. The derivative of negative 3x is negative 3, and then when determining the derivatives, that 1 falls away. And so this is our derivative. And for our last question, this one's really cool. What we're going to do is find the, this is our second last question. This one's not too cool. It's the last one that's really cool. What we're going to do is we're going to find the equation of a tangent line to a curve. In order to get the equation of the tangent line, we're going to need a slope and a point. Well, the slope is going to be determined by getting an expression for the derivative and subbing the x value in. A point on the curve is going to be determined by taking that x value of 4, plugging it into the function expression, and coming up with a y coordinate. So before getting the derivative, let's do that. Let's figure out the actual point on the curve where x equals 4. At x equals 4, y will equal 4 cubed plus 2 times 4 squared minus 4 times 4 plus 1. That's equal to 81. So we know that at x equals 4, the y coordinate is 81. In other words, our tangent line will be going through the point 4, 81. Let's get the slope, which means let's determine the derivative. So using the power rule on x cubed, we get 3x squared. Using the power rule on 2x squared, we get 4x to the 1. Using the power rule on negative 4x, we get negative 4. And then that positive 1 falls away. So our derivative is 3x squared plus 4x minus 4. Let's determine what that equals when x equals 4. At x equals 4, y prime will be 3 times 4 squared plus 4 times 4 minus 4, which is actually equal to 60. So I'm going to now determine the equation of a line with a slope of 60 that goes through the point 4, 81. Y equals 60x plus b. I'll temporarily sub in a y value of 81 and an x value of 4. I can say b is equal to negative 159. And then I can say that the equation of the line is y equals 60x minus 159. Now, this is the question that I think is really, really cool. What we're going to do in this one is figure out the points on the curve with horizontal tangent lines. Let's think back to our advanced functions course. We see that we've got a third-degree polynomial curve with a positive leading coefficient. We have n behaviors in these two quadrants. And so since it's a cubic, I probably have two turning points. I'm going to have a function that looks something like this. I haven't determined exactly where the x-intercepts are, but it's going to look something like that. Now, we're going to try and determine where the tangent lines are horizontal. Well, the tangent lines are horizontal at these 2 points right here. Right up there and right down here, we have horizontal tangent lines. Those 2 points have something in common. One's a local maximum and one's a local minimum. In other words, one's the top of a hill and one's the bottom of a valley. So that local maximum and that local minimum, and this is often the case, both have horizontal tangent lines. So if we can find out what those points are, we're going to know the local max and the local min. We're going to be able to draw a pretty decent graph. Okay, cool. Well, how can we do that? Well, think about it. A horizontal line from grade 9 math has a slope of 0. That means that the derivative will be equal to 0. So all we have to do is figure out the derivative of this curve, set it equal to 0, and solve for x. That method that I just said is going to be something you'll do a lot in this course. You'll determine the derivative, which is 3x squared plus 4x minus 4 using the power rule on that third-degree polynomial. Now that you have that derivative, we're going to set it equal to 0. How do we solve that? We use a little grade 10 math. We factor. And we solve. If 3x minus 2 is equal to 0, then ultimately x is 2/3. And if x plus 2 is equal to 0, then ultimately x is negative 2. So I'm going to take an x value of 2/3 and I'm going to plug it into the expression for y. Y will equal 2/3 quantity cubed plus 2 times 2/3 quantity squared minus 4 times 2/3 plus 1. And that's going to be negative 13 over 27. Then I'm going to take this x value of negative 2. I'm going to plug it in for y. So I'm going to plug it in for x and determine what y equals, I should have said. And that's going to equal positive 9. And so what I get is from this first one, I get that the point 2/3 comma negative 13 over 27 has a horizontal tangent. Well, that's this point down here, that local minimum. And the point negative 2 comma 9 has a horizontal tangent. And that's this point up here, the local maximum. So when it comes time to graph curves, we already know how to determine end behavior. We know how to determine intercepts from solving that third-degree polynomial, perhaps by using the factor theorem or however we do it. And now we also know how to determine the maximum and minimum points by setting the derivative equal to 0, solving for x, plugging that value back into the function and getting y. Using all that information, we're going to be able to graph some pretty good curves in the future.